All right, thank you. One of the things that Tamara and Ming talked about in their presentation for the Moderia meeting, one of the goals is to do validation, and in particular model-to-model validation or data-to-model validation. And Los Alamos National Laboratory is arguably the heaviest sampled 40 square miles on the planet. We've got a ton of data, and certainly it's a potential opportunity to then do some validation work with our models. And so what I'm going to talk about today in particular is talk about resuspension modeling, the air pathway for many long-lived radionuclides, and in particular in arid and semi-arid environments. The air pathway is one of the predominant dose pathways. And so we wanted to look at this in a little bit more detail and again use some of the Los Alamos data to do that validation with. But we also want to talk about a little bit of the discussion that we had yesterday on acute events, because that can be a game changer, especially if you're starting to think out into thousands of years. And so I want to address that as well. Maybe I will go a page down. Okay, so we do know something about wind erosion, and for sure in the upper left-hand corner you'll see a picture of the Dust Bowl. That certainly brought wind erosion into the forefront. I kind of feel like, so we had modeling yesterday of surface water runoff and water erosion. Wind erosion I kind of think of as the Rodney Dangerfield of erosion, because we have whole fields of hydrology, tons of science has been done there. Wind erosion, when I went to do my PhD on this, I couldn't find anybody in a university that really spends time looking at wind erosion. So it's a Rodney Dangerfield, you get no respect, but we do know something about it, it's important. So that's the upper part. The Dust Bowl certainly brought it to the national attention. Right below that is a picture of vegetation covers, or basic vegetation cover drives wind erosion. And you can see in that picture the dust cloud in the distance. This is in Texas, and it's more recent. And you'll see the field there with the grass. No dust is coming off of that, but the plowed field right next to it is just a huge dust cloud coming off. Okay, the important thing when we're starting to think about into the future is vegetation changes. Vegetation cover is very dynamic. Our land use is very dynamic. And bad things happen. Okay, so like the Cerro Grande fire, see the plume there, the fire. Okay, that burned over about a third of the National Laboratory, or Los Alamos, and it burned over thousands of potential release sites. So potentially we've changed our transport rates, right? So you have to be thinking about that. Things change over time. And because of this changes, you can potentially have these deleterious health effects. And that's particularly what we're interested here. Okay, so we've already talked about Area G. This is another one of these heavily sampled sites. We need to do resuspension modeling for these kinds for legacy sites. And we have to think, we also do emergency response, and so if you had a release of material into the environment that deposited, we would be doing resuspension modeling for that. And we have to also think about long-term performance assessments. One of the things that wasn't pointed out, because you saw several of these kinds of pictures yesterday, look at the vegetation around that site. Okay, Area G, you can see it's mowed down, you've got grass growing in, it's a lot of construction, you've got roads there. Look at the vegetation on the outside of it. That's the natural condition for these canyons and mesa tops. You got pinyon and juniper in there, and chamisa and shrubland. Okay, so ultimately, when this site is closed, it will go back to that kinds of vegetation, right? Until the next fire comes along, and then things could change again. And so that's important when you're thinking about resuspension. You have to think about what is the ecosystem that we're interested in. You could have anything from a grassland, which is like, for example, on top of that mesa where Area G is now. You can have shrubland. This is a picture down at Whip. You can have woodland. And you can also think of two other extremes here. Above the grassland, you could think of a desert environment like the Sahara Desert. These are huge dust producers. Or on the other end of the woodland, you can think of a forest where you have very little wind erosion. But within each of these ecosystems, you have a lot of vegetation dynamics. So you can, for example, when Area G closes, they're going to shut everything down, and that vegetation will start off as grassland, right? But then it will then go into shrubland, into woodlands. And then within that time frame, over 1,000 years, you can have different kinds of environmental events or disturbances that will reset the successional clock. So you can have, for example, surface fires, you can have crown fires, or drought. And drought is an important one to consider because what it will do is it will bring on the bark beetles. And when the bark beetles come up, they kill everything, and the trees die off, and you get more wind erosion. Land use is also very important. This is a picture of, I don't know if anybody in here is from California for sure. We've all visited California. This is Owens Lake, and it was painted by a guy by the name of Albert Bierstadt in 1870. Albert Bierstadt was one of these explorers that went with the early expeditions to the west and painted pictures. And then he sent it back to the East Coast to the magazines for publication. And this is a picture of Owens Lake in California that he painted. Owens Lake sits at the base of the Sierra Mountains and collects a lot of rainfall. So it looks very idealistic. The problem is that it was also upstream of Los Angeles. And as Los Angeles was growing, they said, hey, you know what, we need a lot of water for our growing town. And so they started diverting water from Lake Owens in about 1913. And this is an aerial picture of it now on the left. And you can see now it's just a dry lake bed. But the mineral deposits there are quite thick. And now it is one of the largest dust-producing sources in the United States. And a lot of this dust contains a lot of minerals, including arsenic, which is, of course, a potential hazard, right? So what we do with that land over the next 1,000 years can make a big difference. Okay, so resuspension models. These are very simple. I mean, the groundwater models and the surface runoff models, I bet you're jealous because these are very simple equations for us that we use. Okay, so we got two basic ones, right? And the whole model is right here in this simple equation. Okay, we're trying ultimately to predict the concentration in air, right? So that's just simple. We got two different models, the mass loading model and the resuspension factor model. The mass loading model is essentially you're predicting the concentration of air in becquerels per cubic meter. And it's just a simple, once you know the concentration in soil, you're going to say, I know that value, and then I know what the air concentration is in micrograms per cubic meter, and multiply those two together and you can get concentrations in air. There is an area factor in case the area that's contaminated is pretty small. Just some fraction of the airborne dust will be contributed from that particular site. So it's essentially an adjustment factor for the fact that you have a small area. The resuspension factor model is down below it, and in this case, the concentration of soil is not in becquerels per gram, but it's in becquerels per square meter, and you multiply it by a ratio that just takes the ratio of the concentration in air divided by the concentration in air divided by the concentration in the soil. A lot of empirical work has been done, so oftentimes in our business, we use e to the minus 9 as that resuspension factor. And that's based on some work at the Nevada test site. Okay, but you can see that, so these equations are very simple in concept, but there's a lot of complexity behind them. So the concentration of dust in the air can vary orders of magnitude, okay, depending on wind conditions, depending on vegetation conditions and so forth. So that can vary dramatically. The resuspension factor model also has the same kinds of issues associated with that. So when you look at the literature, 1 e to the minus 9, it could be orders of magnitude different depending on the situation. So in dose assessment, if we're within a factor of 10, we're happy. But if we're off by 3 orders of magnitude, then all of a sudden we're very nervous and we're not so happy. So let's go to some of the data we wanted to validate the computer models and see if they actually match up with our data. So here's one of the more contaminated sites at Los Alamos. This is Hillside 138. It actually sits, the building right above it, I think is, oh, that's the motel. Okay, it was a former motel there. And so it's a fairly small area. It's about 100, 200 feet on a side. And we have a sampler that's located just on the downwind side of this particular area. Plutonium-239 contamination, and I'll show you what the data shows. So we know what the air or what the soil concentrations are, and we can then go through our mass loading or resuspension factor models and compare it to the actual measurements of air, in air. So unlike the groundwater folks, we can actually do this kind of validation, which is kind of nice. So we're going to do that one. And then we're also going to just look at, so we know what the concentrations of naturally occurring uranium is in soil, and we measure above that, and this is big, huge areas as opposed to a small area, and then we should be able to match up. So our air samples should match what our soil concentrations are. So that's the other validation we wanted to do. Okay, so here's our validation approach. We looked at the plutonium-239 statistical distribution in the soils, and we also looked at the U-238 concentrations regionally. We took the air measurements from our samplers, and we compared it to what the model would predict. And so these are the results. And so the AirNet Station 324, that's the Hillside 138 data. And below that, in the table below that, is the regional station. So we'll just start with the AirNet Station 324. These are in the far left, the different statistics that we looked at, because there was some discussion. I mean, we talked about how conservative should you be. Should you use the maximum soil concentration? Should you use an average? Or should you use the median? Because, of course, these distributions are often skewed. So you use an average, of course, it's going to be heavily influenced by the higher values. So we just kind of did that comparison. There's mean, median, and maximum. These are the plutonium-239 concentrations. 14 becquerels per gram is the mean, median 1 becquerel, and the maximum is 270. So you can see it's a very highly skewed distribution. And then these are the predicted values in the next column over. The ML is the mass loading approach, and the RF in the next column is the resuspension factor. So these are our predicted values based on those two models, and these are in becquerels per cubic meter. And then we compared it to the next column over, which is the measured becquerels per cubic meter that the AirNet station actually measured. And then these are the ratio between the predicted and the actual for the mass loading approach and the resuspension factors. So you can see we can range anywhere from a factor of 4 difference, which I'm very happy with, to 400, which I'm starting to not be very happy with, okay, depending on what statistic you use. And so it makes perfect sense, because of this as being a skewed distribution, that you would want to use the median in this case. Okay, that would be the one that would give us the closest estimate. We could be way over conservative if we went with the maximum value. Okay, regional stations, similar kinds of layout in this table. Mean, median, maximum. These are the uranium-238 soil concentration, just naturally occurring uranium. The predictive values for the mass loading, resuspension factor, and then what the measured values are. And you can see we're within a factor of 2 or 3. So yay, okay, we're very, very happy with that. That seemed to match up pretty well. Okay, so some of the things we learned. It is important to consider the spatial extent of the contamination. If we took that small little 100 by 100 foot area and we did not take into account the fact that it's a small area, we would have been off by a factor of about 5 times this. So at best, we would have been within a factor of 20. Okay, so it is important to conclude that if you have a small area, you need to account for that. The next thing is use your median, especially in skewed distributions. And this resuspension factor of 1e to the minus 9 that we use ubiquitously is not bad for this particular environment. Okay, so then we're happy. Los Alamos is great. Our models are within, we understand the limitations of them a little bit better. But then we have to start thinking, okay, now we're going to have environmental disturbances that we have to throw in, because we have to model this, like at Area G, out to 1,000 and perhaps even 10,000 years. A lot's going to happen in that time. Picture of the Cerro Grande fire on the left, and on the right, that sign, which you probably can't read, it says, "Danger, keep out explosives." Okay, so these are the areas that this fire swept over, and with different kinds of soil contamination. How does that going to change our resuspension transport rates? So we did a lot of modeling because we knew that that was a key component to driving our resuspension, is what is the vegetation going to be like. And so we went to the literature and looked at resuspension or wind erosion studies and a whole variety of different environments, and you can get this kind of relationship where you have vertical dust flux on the y-axis in relation to the woody plant cover on the x-axis. And you can see it's a pretty good relationship, but within that you have disturbed and undisturbed sites. Okay, so if you just take a grassland and you disturb it and you turn it into for example, an agricultural field, you're going to all of a sudden your wind erosion rates go way up. So within each of these different categories, on the left you have grassland, and then you go into shrubland, then into woodland, and then on the far right would be forest. So we use this empirical data, and we built a vegetation moderated transport model, which allows succession to happen. It allows disturbances that you can put in probabilistically as far as occurrences. And so this is just an example of the output on the far right. And what we have here is on the x-axis we have a normalized plutonium contamination in soil, normalized to 100. And the green line represents what the soil concentration is on site. And so as it goes down, it means that this material is being transported off site. This is not a waste situation. The contamination we're assuming in this particular model was on the surface. So you can see that it goes down initially after the area G is transferred from a grassland, and you have succession into a woodland. And so then it's pretty flat for quite a while with the green line. And then see those red vertical lines? Those are fire events that happened. And you can see the green line, how they dip pretty dramatically right when that happens. And so it does make a big difference. And this is just a crown fire. So on top of this, then we're going to have grass fires, or the ground fires. We also have droughts. And so when you do that kind of data, everything changes again. Again, the key for driving the resuspension rates are the percent of woody vegetation. And so I have a plot here, percent wood cover as a function of time out to 1,000 years, with disturbance is in the gray, and without disturbance is in the green. And so you can see it makes a huge difference, because when you start adding these things, it's hard for that woody vegetation to become dominant. Okay, so it makes a big difference from woody vegetation. And so how does that translate for off-site transport of dose, or of contaminated soil? And so we have the normalized soil concentration with and without disturbance. If we assume no disturbance throughout the 1,000 years, you'd get the plot up on top there in the green, which basically says all the material is going to stay on site. If you throw in disturbances, you get the gray plot here, and you can see it's a dramatically different result. So you have to be thinking about the vegetation cover. Okay, so let me just conclude. The basic models of resuspension, they're simple, they're easy to use, we use them all the time, and they give us a pretty good estimate of what's going to happen, and it worked for the Los Alamos site. There is some understanding that we have to use the median rather than some of this more, especially in skewed distributions, use the area factors, as I said before. It's useful for long-term averages for air concentrations. If you have acute events like wind erosion events, then there are other models that you would have to turn to. These are more average, or more useful for long-term averages. The enrichment factors, some people throw in enrichment factors because uranium and plutonium and the cesiums have a tendency to accumulate in the fine organic material, or finer small silt particles, which are more erodible, so some people throw in enrichment factors. I didn't see any evidence that we needed to do that, at least for this Los Alamos soil. Of course, you have to, if you're having a small area, you need to think about where you're putting that monitor, because that's one location, right? The wind's blowing 360 degrees. So you got to be thinking of that as well, especially if you're worried about a particular location, downwind location. And we do need to think, when we're thinking long-term, we need to think of these environmental disturbances. It does make a difference. So with that, I will conclude.
Thank you, Chad.